Imagine a remarkable machine with a level of adaptability akin to that of biological beings, like an octopus that can instantly alter its form and mechanical attributes to match its requirements. Or imagine entering a world where the physical reality seamlessly intertwines with the virtual realm, a place where unprecedented flexibility and creative possibilities are available when designing and manipulating materials. Inspired by these remarkable adaptive features exhibited by biological and virtual systems, soft machines that can tune their shape and mechanical properties have shown great potential in applications involving unstructured and continuously changing environments. However, current soft machines are far from achieving the same level of adaptability as their biological or virtual counterparts, hampered by limited real-time programmability and severely deficient reprogrammable space of properties and functionalities. To address this challenge, here we introduce a pixelated in situ programmable mechanical metamaterial, PPMM, that leverages graphical stiffness patterns to program and reprogram an unprecedented level of versatile mechanical capabilities without requiring additional infrastructure. Inspired by binary language systems, where simple coding of discrete binary digits with assigned coding sequences enables effective and comprehensible representations of a variety of information, we harness stiffness tunable pixels that can be in situ encoded as 0 and 1, where 0 represent the pixel in a stiff, deactivated state, and 1 represent the pixel in a soft, activated state. To achieve this, we employ a synergistic approach that combines the elastic instability of an elastomer with a periodic array of elliptical voids and the phase change of embedded low melting point alloy, LMPA. The LMPA we used, known as Field's metal, is a eutectic alloy composed of bismuth, indium, and tin. This alloy remains in a solid state at room temperature, but undergoes a phase transition into a liquid state at a low temperature of 61 degrees Celsius. This unique property empowers each pixel of the PPMM to achieve dramatic changes in stiffness with low energy consumption. Finally, we integrate soft heaters into each pixel to enable real-time active control of the LMPA and ensure reversibility. Through uploading digitized stiffness pattern information by independently switching the digital binary stiffness states of individual pixels, a PPMM featuring a grid of 7 by 7 pixels can project an extensive range of 2 to the power of 49 possible mechanical information. This abundance of mechanical information encompasses a wide spectrum of mechanical attributes, including shape-shifting, shape memory, stress-strain response, and Poisson's ratio, as well as application-oriented functionalities such as tunable and reusable energy absorption and pressure delivery, all of which can be quantitatively adjusted as needed. For instance, when the PPMM is put under compressive strain, encoding a digital pattern can lead to a distinctive shape-shifting response characterized by tunable continuous curves on both sides of the PPMM. By rationally encoding the digital pattern, we found numerous sets of shape-shifting modes of the PPMM that can be expressed, including stationary, contraction, shear, and flexure modes. Furthermore, their degree of shape-shifting can be further quantitatively tuned by making coherent pattern adjustments. Also, these various attainable shapes can be memorized and retained without requiring continuous energy through time-dependent coding with rationally sequenced digital patterns. For instance, activating the mechanical pixels in the middle 3 horizontal rows and applying compression caused the PPMM to shift into an hourglass shape. Deactivating the pixels while maintaining compression memorized the deformed shape, which the PPMM held without requiring external load or energy. Subsequently, reheating the deactivated pixels restored the PPMM to its original shape from the shape memorized state. The remarkable aspect of the pixelated approach lies in its ability to selectively target the regions for shape memorization. The PPMM has the ability to deform and memorize its entire structure. Alternatively, It can be selectively activated and then fully memorized. Furthermore, it can be selectively activated and then selectively memorized. This versatility of the PPMM opens the door to dynamic optimization in load-bearing applications, since the PPMM can adaptably memorize an effective shape depending on the specific shape of the load it will support. Another quality that can be quantitatively tuned with digital pattern coding is mechanical properties. Since each pixel in a stiff state contributes to a portion of the overall strength of the PPMM, the stress-strain curves can be adjusted in correlation with the portion of the activated pixels. We performed a comprehensive set of 1,200 simulations, with each simulation featuring a unique pattern. As a result, the PPMM showed a remarkable fine tunability, with the effective Young's modulus being inversely correlated with the activated pixel density. As another mechanical property of the PPMM, we explored the effect of pixelated activation on Poisson's ratio, which is defined here as the ratio of the transverse strain to the longitudinal strain. In order to achieve quantitative tunability in Poisson's ratio, we first rationally derived two elemental patterns that produce the two opposing negative and positive values of Poisson's ratio. By combining these patterns column-wisely, each unique mechanism was preserved, allowing for local variations in Poisson's ratio that could be summed or cancelled to produce the overall Poisson's ratio response. As one of the possible applications, we demonstrate the PPMM as a tunable and reusable energy absorption material for an extensive range of possible impact scenarios. In contrast to most existing energy absorption materials that have fixed mechanical properties and attenuate impact through irreversible crushing or plastic deformation, the PPMM features broad-range programmability and reprogrammability, as well as recoverability driven by the phase transition mechanism. For example, in low-impact energy scenario, a highly deformable pattern can effectively absorb energy and avoid the creation of internal stress that can elevate the transmitted stress. However, in higher impact energy scenarios, highly deformable patterns could be less advantageous as excessive deformation can lead to the densification of the structure. For general guidance of the activation pattern, we created a design map that plots the minimum peak transmitted stress for various patterns across a range of impact energies. This illustrates the PPMM's versatility in adapting to different conditions. As another possible application, we exploit the PPMM as an adaptive pressure delivery material that can control the path of stress flows through their mechanical pixels. In detail, when one side of the PPMM is pressed, the pressure can be selectively transferred to specific locations on the other side, depending on the digital patterns. This functionality can be extended to a biaxial basis, in which the pressure delivery path is programmed independently for each axis. To show this capability here, while maintaining the vertical pressure path, the horizontal pressure flow path located at the top of the PPMM was changed to the intermediate position. Lastly, we demonstrate that the pressure delivery can also be chronologically controlled by the activation pattern. The inclusion of a buffer pixel delayed the transmission of the pressure driven by the deformation of the buffer pixel, resulting in sequential pressure delivery and subsequent operation of the LEDs.